All right, today we are going to take a look at polar functions. All right, that's what we're picking up with. So, first question I have for you is what is a polar function? So, a polar functions, what they are functions that use r and theta as variables. This is what we've been going through in the last few days here. Anything that uses r and a theta. So here down, if you look at the equation, notice that you have r is your dependent variable and theta represents the independent. Okay, so I gave you two forms here. Most of them will come in that form. Now, by the way, there is the option of just having the equation such that like r equals theta, that would where there's no sine or cosine. But for the most part, we typically have either a sine or a cosine, and the variables out in front, you would have like an a and a b. It's a being a constant, b being coefficient, and n within the sine or cosine function if you have a rose with multiple petals. So that's the form, and that's what a polar function is. So quick hit. Is this a polar function? What I've written there. Yes or no? Is that a polar function? Y'all are going to have to come off mute. Is that a polar function?
No.
No, good. That's not polar. That would be a trigonometric function, but it's not a polar function because it's not in the form of r, having an r and a theta. So just want to make sure we're clear on that. That is a trigonometric function that's not polar. That's not polar because it's not an r and a theta. Whereas these would be polar over here. Okay, one other basic thing to get down before we dive into this is here's how you convert from one type of equation, a rectangular equation, to a polar equation. We're going to use these formulas. That cosine theta is x over r, that ratio that we've been talking about ever since we came back from Christmas break. That sine is y over r. That tangent's y over x. So sine is y, cos is x, tangent is y over x, is what you've heard me say so many times about the year. And the Pythagorean identity that x squared plus y squared equals r squared. And what you could do to isolate different variables specifically is we could say x equals r cosine theta. Now that's just because all I do there is I take this equation right here and I multiply both sides by r. And we come up with that equation. I'll remind you that y equals sine theta equals y over r. We can say that y equals r sine theta just by multiplying both sides of the equation by r. Now, when it comes to the tangent function, how we manipulate that one is we actually would take an inverse if you needed to isolate the theta. So those two correspond. And then finally, if you wanted to solve to get r isolated in the last equation, all you do is take the square root. Okay, so there's the basics of how we're going to convert from one form to another if we need to do so, and which we will tonight. I'll actually begin there. So first, with polar. The things I want to remind you of is how do we plot polar coordinates. So again, in all of these problems, we're talking about that being the r value, this being the theta. And so how I'm going to do this is first for the plot 4 pi over 3, excuse me, point A, which is 6 comma 4 pi over 3. What I'm going to do is go to 4 pi over 3. So 4 pi over 3 is on this angle here. I'm going to draw what's technically called the vector. Now that's going towards 4 pi over 3. And if I have the number 6, what I do is I go out to the 6, 0 on that line. So 1, 2, 3, 4, 5, 6. This point right there would be point A. Now, how this can start getting confusing is when we start throwing in negatives. So we're so used to it all of our lives when we've dealt with coordinates that were in the form x comma y, that a negative for the x means go left and a negative for the y means go down. But that's not necessarily the case in polar. So what the negative means when you're talking about the r being negative is it doesn't mean go towards 5 pi over 6. This would be go away from 5 pi over 6. So here's what's called a vector pointing at 5 pi over 6. But if I have a -3, what I actually go is 3 circles away from 5 pi/6. So I don't go towards it. I go 1, 2, 3. This point right there would be point B. Now, what is different when it comes time to do a negative angle? Well, with a negative angle, what that means is I don't go towards 3 pi/2. That, by the way, 3 pi/2, I want to go to the second circle because that's where this one's going to be. 3 pi/2 represents how many radiuses it takes going around the circumference of a circle. So in this case, that would be positive 3 pi/2. So what negative 3 pi/2 is negative 3 pi/2 would be on the second circle going the same amount of distance, but this direction. So negative 3 pi/2 would be right there. So you go around the circle to that point, and because it's on the second circle, that would be where C is located right there at that point. So I went negative 3 pi/2 of distance around the circle, and that's how I got there. All right, and now finally, the last one, D, -pi/4. So -pi/4 is coterminal. There's a big word you need to make sure you know. I could say that is coterminal. They're the same point as taking -5, and I could add, whoops, I forgot to write -pi/4. What I could do if I wanted to work with these negative angles is you can add 2 pi. I just want to remind you that at any time, adding a full circle doesn't change your value. So if I got a common denominator there, that's the same thing as -5, comma, -pi/4 plus 8 pi/4. Because quickly, what is 8 divided by 4? What is 8 divided by 4?
2.
2. So 8 pi/4 would be 2 pi. And so one more time, how I could write this is -5. And when I combine the terms there, I get 7 pi/4. So a -pi/4, I'm going to go to the fifth circle, 1, 2, 3, 4, 5. -pi/4 is the same thing as being at 7 pi/4. So there it is. But because it's -5, I actually go 5 circles away from it. So it'd be 1, 2, 3, 4, 5 right there. That would be the actual location for point D. That's 5 circles going on that the line there at -pi/4 or 7 pi/4. So that's how I get to point D. So my final location points here, that's D. C, A, B, and C and D are all now properly graphed. So by the way, all this stuff is extra. I don't need that on the graph anymore. I wouldn't need any of those points remaining on the graph. So I can take them away to show you where each of those points is located. Just to clean this up a little bit, that's where all the points are located. Okay, so just as like in closing, a pi, what that's doing is it's measuring radians, which I'm just going to say radii, around the circumference. That's what a pi actually is. And so the theta is just telling you how far to go along the circumference, and the r is telling you which circle to be on. Okay, so that's what that is. All right, now let's talk about converting from polar coordinates to rectangular. So one more time, if it's polar, this is in the form r theta. My question is how to go to rectangular, which rectangular is x comma y. How do you think we could take an r and a theta and change it to x and a y?
The square root of x squared plus y squared.
Now that's a good idea if we needed to find r squared or r. We actually know what r is. So that's a good idea. You're on the right track, but that's the wrong formula. We're going to use a different formula. So keep thinking. We're trying to turn it into an x and a y. There's your hint. What other formula could I use?
Is the x equals r cosine times theta,
That's it.
and then the y equals r sine theta.
There you go. That's the one. Because we're looking for x and y. That formula isolates x and y in terms of r and theta. Perfect. So here's what I'm gonna do. I'm gonna do a column for my x here, and I'll do a column for y over here. So what I would do is I would say x equals 6 cosine of 4 pi over, 4 pi over 3. And my y is going to equal 6 sine of 4 pi over 3. Now, the thing I want to make sure you don't mess up on is values are going to go positive and negative based off of where they're located on the unit circle. So 4 pi over 3, what quadrant is 4 pi over 3 located in? Is it in quadrant 1? Yeah, I heard
third
some.
quadrant.
That's right. Because it's more than 1 whole pi, but it's not yet close to 2 pi's. So it's in the third quadrant, and pi over 3 is closer to pi over 2. Or in this case, closer to 3 pi over 2. So 4 pi over 3 is over there if you want to be accurate. Which means what for my x's? Are my x's greater than 0 or less than 0 when I'm on the left side?
Less than 0.
Less than 0. And what about y's? Are my y's greater than 0 or less than 0?
Greater than 0.
Nope, nope, nope. It's going down.
Oh, the third one, right? Negative.
Yeah. Yep. So they're both negative. So now we can use our hand trick. So 4 pi over 3. Which finger is our pi over 3 finger?
The index.
That's right. Bend your index, flip your hand over. And we have that this is 6 times. What do you have for cosine there? We know it's negative. That's right. Negative 1 over 2. Which that's going to be 6 times negative 1/2, which means it's negative 3. And now let's go do the y here. The y value would be 6 times a negative square root 3 over 2 at that location. So that would equal negative 3 square root 3. And so our point A is equivalent to negative 3 comma negative 3 square root 3. There is point A converted. Okay, now from there on, all these problems are going to work exactly the same way. It doesn't matter if you have a negative or positive, it works the same way. So here on this next one, if I wanted to do x equals negative 3 cosine of 5 pi over 6, again, I'm going to think about 5 pi over 6. Let me go ahead and write on the sign there. Negative 3 sine of 5 pi over 6. So once again, I want to draw a unit circle here. 5 pi over 6 is located in which quadrant? Where's 5 pi over 6 located?
Second quadrant.
That's right. So in the second quadrant, what can you tell me about x?
X is negative and y is positive.
X is negative. I agree. Y is positive. I totally agree. Good job. So when we go to simplify this, pi over 6 finger is your index finger. Bend your index finger. Flip your hand over. And so here I have negative 3 times. This will be negative. How many x fingers do you have there?
3.
Yeah, square root 3 over 2. Which is going to equal positive 3 square root of 3 divided by 2. And then over here for y, I'm going to have a negative 3 times negative 1/2. Nope, not a negative 1/2. I'm sorry, I messed that up. Let's start that one again. Sine, we said y is going to be positive. So this will be negative 3 times positive square root 1 over 2. And so that would reduce to be negative 3 over 2. And so my point on this one, this is equal to 3 square root of 3 over 2, comma, negative 3/2. That would be point B. Questions so far? Okay, I want to do one more and then I'll let you do D as DOL. So let's start with C here. Let me use blue here. So X is going to equal 2 times the cosine of negative 3 pi over 2. And Y is going to equal 2 times the sine of negative 3 pi over 2. So let's go to our unit circle here. Negative 3 pi over 2, where should that be located? Negative 3 pi over 2, where would that be? Answer is straight up. That would be negative 3 pi over 2. So what can you tell me about the X values if you go straight up? Is my X positive or negative? I'm straight up. Still waiting for an answer here. Is X
Positive?
positive? Good guess. It's not positive. So what do you think now?
Is it 0?
It's 0. There you go. It's a trick question. X is 0. What about Y though? Positive or negative if you're going straight up?
Positive.
It's positive. There you go. It's positive. So what can we do there? Well, we can bend our thumb because this is our thumb. And what we find out is we have 2 times. This is going to be the square root of 0 over 2 or just 0 over 2. And over here, we're going to have 2 times the square root of, if you bend your thumb and flip your hand, square root of 4 over 2, which is the same thing as 1. So this point is going to be 0, 2. That's going to be our point C. Now, here's what I can do to check to see if these are right. These are actually the exact same points that we just plotted. Let's go back a slide. We have A here as being left 3, then down 3 square roots of 3. Notice where point A is. If I counted, here's the x's. That's negative 1, negative 2, negative 3. Now, look what happens when I go down. Is point A left 3 units? I have my markings here.
Yes.
Yeah, negative 1, negative 2. Notice A is left 3 units. How many is it down? Well, you can count it up. The problem is it's not going to be at an even number because it's that square root. It's negative 3 square roots of 3. So that's negative 3 times 1.73 approximately, or 1.72. So that's what that value is going to be over here. If you went and took it to the y-axis, that's what that value is here. Or let's go to B. B, we had 3 square roots of 3 over 2, comma, negative 1.5. If you look over here, B is to the right and down. This is 1. That's negative 2. Notice B is at negative 1.5 on the y-axis. Or take C as an example. We got 0, 2. Notice where C is. It's up 2 units. It's at 0, 2. So we are doing these correctly. It's working just fine. So you're trying to find out what is the exact location of point D there. So I'll let you do this one as kind of a DOL. I'm going to pause this and let you work for a second. We'll call this DOL. You do DOL, and then we'll come back on, see what you get. Okay, so go ahead and try part D. Okay, so picking back up. Now we're going to look at how do we convert rectangular to polar? Well, remember what we just did was we did x equals our cosine and y equals r sine. Now, how you convert the other way is you use that r is the square root of x squared plus y squared, and your theta is the tangent inverse of y over x. Those are the two formulas we're now going to use. So we're not going to use these two. Instead, we're going to use those other two formulas. So here, you can probably think about this point. This is an x, this is a y. But we could take a guess. If you're left 6 units, 4, 5, 6, if you're left 6 units, you could probably take a guess at what that point is. That would be on the 6th radius. At what angle would that be right there? Point F. What point would that be? Or what theta would it be if you were to guess?
Maybe pi.
That's right. Now that's what we should get. Now let's check it. So that's what we're guessing the answer should be. This is our guess. And the way to figure it out is to say, well, r equals the square root of negative 6 squared plus 0 squared. And that is, in fact, the square root of 36 plus 0, which is a square root of 36, or 6. So that part is right. And then what you do for your theta is you take tangent inverse of y over x. Because this is in the on the left side of the graph, the inverse of tangent, I want to remind you, is restricted. And so since the inverse of tangent is restricted like that, you'd have to add a pi to go left. And if you type in the calculator and you press enter, what you'd find out is the tangent inverse there is 0. And so it's 0 plus pi, which is just going to equal pi. So we did do it correctly. Okay, it looks like I have some type of formatting error here, switching over my iPad. That's supposed to be a square root, a negative square root of 3, 1. So if we thought about this one, we're going left and then up. So we're somewhere in the second quadrant. That's where that point would be. So let's figure out what this value would be. It'd be r equals the square root of negative square root 3 squared plus 1 squared. All right, help me out. What happens when you square the negative square root of 3? Well, negative times
away the square root.
That's right. And the negative also cancels because the negative times the negative is positive. So that just becomes 3 plus, and what's 1 squared?
1.
1. There you go. Thank you, Evelyn. Hey, where are my two guys? If y'all can speak up here. If y'all want to get credit, I need y'all participating with me. So this is the square root of 4, and the square root of 4 is finally 2. So that's our r. Now, if I wanted to find my theta, I would do an inverse tangent. Again, since this is on the left side of the graph, I'm going to have to add a pi to the value, but it'll be this 1 over the negative square root 3 because it's y over x. So we could use hand trick on this one because 1 is the same thing as like the square root of 1. So I could do, if you look at the back of your hand, you want 1 y and 3 x's. So which finger are we bending?
Ring.
The ring, that's right. I'll flip it over. The ring is a pi over
6.
That's right, pi over 6. But the problem is because this is a negative, that means it's a negative pi over 6. And so then we just add a pi to that as part of the restriction. And so a negative pi over 6 plus 1 whole pi is going to equal 5 pi over 6. That should be the angle in the second quadrant, which it is. So we're good. That is our answer, 2, 5 pi over 6. That would be my second answer there. Okay, I'm going to do one more with you. This is also one that we could guess. If you think about 0, negative 4, that means you go down 4 units. So if I go down 4 units, what radius am I on?
The pi over 2. Or
that's the
pi
theta. It'll be 3 pi over 2. That's right. So it'll be the fourth circle at 3 pi over 2. You're correct. That will be the point. Now, what you could do, though, if you need to, is the square root of 0 squared plus a negative 4 squared. Negative 4 squared, which is going to equal the square root of 0 plus 16, which will finally equal the square root of 16, which equals 4. So we were right on the radius. And then if you did your inverse tangent, since it's on the axis, you're fine as far as the restriction goes. You don't have to do anything, but it's the negative 4 over 0. Can we divide by 0?
No.
No, this is undefined. That's undefined. You are not allowed to divide by 0, so it's undefined. Those places where tangents are undefined is at negative pi over 2, positive pi over 2, and any recurring pi amount. So since it's undefined, theta is either negative pi over 2 or positive pi over 2. Looking at the graph, it has to be negative pi over 2. Therefore, let me do a therefore, because that's where inverse tangent is undefined. This would be negative pi over 2. So we were right. Negative pi over 2 is the same thing as 3 pi over 2. Negative pi would be going, negative pi over 2 is that way. 3 pi over 2 is going around that way. That's 3 pi over 2. This one's negative pi over 2. Same thing. Okay, I'll let Jay be one for you to practice. If you want to try to do your math real quick, see what you come up with.
Just where he's. I have a question.
Yep.
For whenever you, well, you know how tangent has a restriction, sorry.
Yep.
Can you base it off like the rectangular coordinates? Like it's a negative in X and a positive Y, that would be in the second quadrant. And then you know how we got pi over 6 with the
Yep.
hand trick? Could we base it off that? Like I know 5 pi
Yes,
over
you
6 is in
could.
the second quadrant.
Absolutely.
Okay.
So once you know it's a pi over 6, and you know it's in the second quadrant, you know it has to be 5 pi over 6. That is 100% true.
So adding the pi, like you don't have to do it. You could just base it off the
Yes,
quadrant.
that's correct.
Okay.
So how about this one? We'll just pick it up and we'll do it that way. So if I wanted to find my r, I'm going to take the square root of 5 squared plus 5 squared. Well, what is 5 squared?
25.
That's right, 25 plus 25, which is the square root of 50. The problem is we don't have a good square root of 50. So I could reduce this, but how I would reduce it is I would say this is the square root of 25 times the square root of 2. What's the square root of 25?
5.
So it's 5 square roots of 2. Now that's our r. Now to get the theta, it would be the inverse tangent. And by the way, we're using your trick. 5 comma 5, that's in the first quadrant. So we know we're in the first quadrant. Would be tangent inverse of 5 over 5. Well, what is 5 divided by 5?
1.
1. Which you can also write it as the square root of 2 over the square root of 2. Now, why did I do it that way? Because you can do this on the hand trick. Hand tricks when you have a total of 4 fingers, and square root of 2 divided by square root of 2 would leave me 4 fingers when that's a y and an x. So if you flip your hands over, you need 2 y's and 2 x's. So I bend my middle finger. What is your middle finger?
The pi over 4.
That's right. It's pi over 4. And since we're in the first quadrant, do I need to alter pi over 4, or is it good as it is?
It's good.
That's right. And so that would be the answer. Pi over 4. 5 squared roots of 2, comma, 5 pi over 4. Okay, so that was a whole bunch of points. For the AP exam, from you looking at release questions, that's going to be the key for polar, or being able to do those. That's going to be the majority of the test, either plotting or converting between polar to rectangular or rectangular to polar. That's like the biggest part of the real test. From what has been released, I should say, are these type of questions. But having said that, I want to make sure we're aware of how these graphs work. So here's what I want you to do. Scan that QR code on your cell phone, or if you're on your cell phone right now, let me post that link into the chat. If I can here. So give me just a moment. Well, I'm having a hard time doing it. I'm trying to do it from my phone. Whoops. That's not what I wanted. What I want to do is take this. Well, let me copy this. Okay, how about this? If this isn't working, here we go. Well, it's not working for me. I'm sorry. Whoops. I posted this link in the Google Classroom. If you go to Google Classroom, you can see it if you're on your phone right now. But if you're on your computer, just scan this with your phone, okay? It should open up this graph. And here's what I want to do. I want to tie in, for most of the remaining time, how a polar graph, that's what you're looking at right now, you're looking at a rose, how a polar graph corresponds with its equivalent trigonometric function. So what I have here are two different graphs, and I'm going to show you this. I'll be alternating back and forth here. That this right here is the equation right here, what you're looking at, the blue, is y equals 5 sine 4x. Okay, now that's what I have in blue right here. When I'm clicking it, that's y equals 5 sine 4x. That's what that graph looks like. Now, what I'm going to do is convert it over here in polar form. What you're now looking at is r equals 5 sine 4 theta. And I want you to notice the difference. I'm going to start with the rectangular form. So what I want you to do when you open up this graph, how many are y'all all have this open up?
Yeah.
Yeah.
Okay. What I want you to do is turn off the orange, line 2, turn that off, and turn on the line 6. It'll be a blue circle. If you want to change the graph to look rectangular, what I'm going to do is hit the settings in the top right. And on the grid, there are two different ones. I'm going to click the rectangular. Okay, so looking at the blue, here's what the first observation I want you to look at. How many, whoops, that's not what I want to do. How many maximums do you see on this blue graph here? On this blue graph, how many maximums do you see?
4.
1, 2, 3, 4. Very good. And how many minimums do you see? 1, 2, 3, 4. So there's 4 maximums, 4 minimums. Everybody good there? Now, next thing I want you to account. How many x-intercepts do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So how many maximums do we have?
4.
How many minimums do we have?
4.
And how many x-intercepts do we have?
9.
Okay, now that we
4.
all have these numbers, what I want you to do is turn off the blue and turn back on the orange, line number 2. And I'm going to switch my grid back to being a polar grid in the settings. Now I want to check this out. What I'm going to do is I'm going to start sliding my angle so that this purple dot moves around. And I want you to notice that I have a maximum right there. You see that maximum? There's my first maximum. And I want to keep sliding it. And as I go around, now this is actually going to be a minimum. Now, how do I know this is a minimum? Well, by order of that function, when you're looking at rectangular, it went to a maximum first, and then it went to a minimum. That's one reason. Well, another reason is if you look out here on the outside where I'm trying to touch right now, you should see the screen flashing at you. That blue dot out there is just tracking with where we are, where our theta is. This is a maximum because it's, whoops, went too far. This is a maximum because my purple dot is pointing at my blue dot. This is a maximum 5 units out. It's 5 circles out. That's because the equation right here has a 5 right there. That 5, if I change it, I can make it a 6 to make it bigger. I'm going to leave it as a 5. Because it's pointing at that blue dot, that's a maximum. Well, I keep going around, and now my angle, notice my purple dot goes around and through. This is a minimum because my purple dot down on the bottom left is on the opposite side of where my angle actually is in the upper top right. Notice they're pointing away from each other. So this is that first minimum. Well, if I keep going around, notice this would be a maximum. Again, it's a maximum because we're pointing at it. Maximum, maximum. This would be a minimum. Whoops. A minimum because I'm pointing away from it. Is this making sense to you? So as I tie in my two graphs, I'm going to have another maximum, minimum, maximum, minimum, and I've gone around the circle. So how many maximums were there?
4.
That's right. And how many minimums were there?
4.
4. Because of that, how many petals do we see on this rose?
Eight.
That's right. Because if you look at this graph, there were 4 maximums in blue. There were 4 minimums. Together, they made 8. Now, what are zeros in a polar graph? So each one of these was the maximum or the minimum of a petal. The maximums and minimums together make up those petals. But now let's talk about what are zeros from a rectangular graph. What a zero is when the graph intersects what we call the pole. Every time we get what's supposed to be a zero, let me turn this on real quick to find a zero. We're supposed to have a zero at 3 pi over 2, for example. We're supposed to have a zero in blue. It says we're gonna have a zero at 3 pi over 2. What that means is on my polar graph, if I went to the angle 3 pi over 2, so I'm watching this blue dot down here until it gets to 3 pi over 2. If I get to 3 pi over 2, I'm going to be at the pole. You see how at 3 pi over 2, it hits the pole? The pole is what you call the origin on a polar graph. You see how we're at the origin there? That would be an x-intercept on the rectangular graph. Or if I went to another polar, another time we intersect the pole right there, 5 pi over 4. That's it. Whoops, let me get there again. Goodness, stay on there. Right there. That's at 5 pi over 4. Notice when the blue's on 5 pi over 4, we're at the pole again. What that would mean is on this blue equation, at 5 pi over 4, I must have a 0. Let me find it. There it is. 5 pi over 4, I have a 0. Does that make sense how these graphs are working? So now let's go change my equation. I haven't heard from you. Are you following or are you lost?
I'm good.
Okay.
I'm good.
All right, here's what I want you to do. On the equation, I want you to put 2 plus 5 sine 4 theta. I think this one might help us out, making it, this looks a little bit more like a butterfly to me. Okay, do you see how, if you have this equation in 2 plus 5 sine 4 theta, notice it doesn't look like 8 even petals anymore. Now let's talk about why. Turn off the orange and turn on the blue. Now, why is it that we don't have evenly spaced petals? Well, because we have a vertical shift now. The midline has been shifted up 2 units. So you can ask yourself, how many maximums do we have?
Still 4.
Still 4. Nothing's changed. How many minimums?
4.
4. But now, guess what's different? The minimum is how low? How low is that minimum?
-3.
Whereas the maximum is how tall?
7.
7. And again, you're still going to have the same amount of zeros, which means the same amount of intersections with the pole. So now when we go back to the orange graph, when we look at this orange graph here, if I go around, notice the maximum values. Each time I get to a maximum, come on, slide out. There you go. Each time I get to a maximum, notice this is on the 7th circle. That purple point is on the 7th circle. It's kind of weird because the circles are counting by halves. But notice if you look at the polar axis, it's between 6 and 8. So it's on the 7th circle. Notice that's a maximum. It's easy to tell now that that's a maximum. Whereas those smaller little circles are the minimums, which occur at, what was it? It looks like -3. Now, how do I know it's negative? Because again, it's pointing away from that angle 3 pi over 8. Do you see how the blue up here does it flash on your screen when I touch it like that? It should be.
Yeah.
Okay, you see how that's on 3 pi over 8? This purple is on the opposite side, so it has to be a negative number, and it's in between 2 and 4. So it's 3. I'm going to confirm it by going here and clicking this minimum. You see how it says 3 pi over 8 is -3? That's how a polar function corresponds to its trigonometric graph, which also brings me to this point now. Do you remember earlier in the year we gave the definition of a function? A function has to be able to pass the vertical line test. Well, you might notice this does not pass the vertical line test. So you could be thinking to yourself, how is it a function if we don't pass the vertical line test? And the reason it's a function, because if you look at this, let me press enter. You might be like going, that would not pass the vertical line test. How could we say that's a function when if I pass a vertical line like that, it fails the test? That graph does not pass the vertical line test. Or if I put it here, it still doesn't pass the vertical line. Why is this a function? It shouldn't be a function. Well, that's because we're looking at it in terms of polar. But if I looked at the equation in terms of its rectangular, do you see how it now passes the vertical line test? So we still call it a function, even though because the blue graph always passes the vertical line test. The polar graph does not pass the vertical line test. But when you convert it to its trigonometric equivalent form, that's y equals, so in this case, it's y equals 2 plus 5 sine 4x, it now passes. Does that make sense to you why we call it a function, even though the polar picture fails?
Yes.
Yes.
All right, great.
Yep.
So we got 10 minutes left. Here's what we're gonna do. We could play around with this some more. It's kind of neat. There are a lot of neat equations you could come up with. Stuff I haven't shown you, like if you just do a theta. And I'm gonna actually make this go to, how about 2000, and I start to zoom out. Check that out. I could try to hypnotize you on Zoom right here. You're getting sleepy, getting sleepy. You can see that's kind of neat. There's a lot of cool graphs you can come up with polar, but all it does, let me see what this would look like. Oh, that's just a straight line. Okay, and rectangular. It's really neat if you play around with this and trying to see different graphs. Remember, how about this one? 3 minus 3 sine theta. There's that heart we talked about. Do you remember the name of this heart?
Is it the dimple or the cardio?
It's cardioid. Cardio means heart. Cardioid. The dimpled one is when it looks like this. If it never actually has a 0 in the rectangular, that's what we call dimpled. Because, and what it means not mathematically, but in rectangular form, if you graphed it, notice, does my blue graph ever hit the x-axis?
No.
Because it never hits the x-axis, when you convert to polar, it never touches the pole, which means the origin. It never touches the origin. But if the blue graph does, let me go back to the heart. If it does touch the x-axis, now we are going to touch the pole. And that's where you start getting a lot of those cooler shapes like that. And if I change it one more thing, and then I'll move on. Okay, so now notice I touched the polar axis 2 times, which means that negative portion of the graph, when the blue graph is below the x-axis, that's going to be a loop that's facing away from its angle. So this loop right here, if I'm right in here, notice that's when your values are negative. In here, this interval of values on this little loop, this starts once the blue graph goes negative. So it goes negative from 0.73 to 2.14. And that's where this down here starts going on that negative loop. That's where that happens. So that's how the graphs work together. So with all of that being said, we won't have time to work as many problems as I have, but we can work one more. Let's talk about how you could graph this if this came up on the test. What I would suggest for you to do first is if you had to graph a polar equation, if I were you, I would start by graphing it, its trigonometric equation on a rectangular graph. So help me out. What's the midline in this equation of y equals 2 minus 5 sine x?
The 2.
Okay, so I wish I had an ID with me here. Oh wait, I do have a tool. What am I doing? Let's go. So this is the goal. We want to graph that. That's the goal. So what I'm going to do here is I'm going to go up to 2. There's my midline. Y equals 2. Now my amplitude on this problem is 5. Remember, this is the midline. This is the amplitude. Because it's negative, we're going to go to the minimum before we go to the maximum. Question for you. Sine. Does sine begin at its midline, or does sine begin at its typically maximum or minimum value?
The midline.
The midline. That's right. And so sine's going to start its midline, and sine reaches its maximum normally. Sine reaches its maximum. Whoops. Let me try that again. Sine reaches its maximum. If you just wanted to fill this in really quick, we go 0. Sine reaches its maximum at pi over 2. Then at pi, it's back to 0, and 3 pi over 2 is its minimum. In this case, because of the transformation, because of the negative, we're going to go to the minimum first. So at pi over 2, we go down 5 units. So 1, 2, 3, 4, 5. I'm going to have this point. At pi, we're back to 0. At 3 pi over 2, we're now at the maximum. 1, 2, 3, 4, 5. And then at 2 pi, we're all the way back around the circle. And so we're back to its midline. Now, if I just kind of make this into a wave, so the wave would look something like this. I have an idea what this should look like now. I'm going to have, whoops, that would not curve right there. I messed up this part because it's going through its midline. That's not the max. That's not the max. It should be coming through like this. Okay, so here's what happens. Starting at 0, at the angle 0, we're out 2 units above the x-axis. Now, as I move around, remember, angles go this way. That's the direction we're moving. As we move, as our angles start getting larger, we're going to go and we're going to have a 0 in here. At some point in time, we're going to hit 0, which means on the polar graph, we're going to go through the polar axis. So as I move around this way, I'm going to hit this polar axis at this point here. Let me color coordinate this. When I get to that point there, when I get right there, wherever that is, that's when this graph hits the pole. Now, you got a question? No? Okay. Now, I'm going to be negative, which means I'm going away from the angle up until pi over 2. So as my angle increases around towards pi over 2, I'm going to approach the value of -3. That's what I'm going to approach. So this value, by the time I get to pi over 2, there we go. By the time we get to pi over 2, we're going to be down 3 units. So 1, 2, 3. I want to put that dot there, and so I'm going to start to draw my arrow connecting to it this way. Now from pi over 2, as I continue my angle forward, as I continue to move past pi over 2 and around the circle this way, what's going to happen is I'm going to go and return to the pole. So my graph, starting from here, as I make this upward trend, is going to return to the pole. So as I go around, it's going to return to the pole like that. Now I'm going to go up, and at pi, I should be out 2 circles. So if I want to be accurate, I'll put that on there. At pi, so I'm going around this way. I'm at 2 circles. I'm going to go all the way out to the maximum, which is 7 units at 3 pi over 2. So at 3 pi over 2 should be 7 circles. 1, 2, 3, 4, 5, 6, 7 right here. And so as I go around the circle, it just keeps increasing, increasing until there. And then it starts to decrease one more time, and it's going to decrease all the way back to that midline value at 2 pi. So it's going to decrease all the way around like that. And that should be my shape. Now that's what we call a limosson in French. which if you want to be Texan, just call it a limacon. And we call this a looped limacon because we're in Texas. And that's how you graph that. Now let's check our work. Let's make sure we're right. So it's 2 minus 5 sine. Oh, darn, meant to ask a question for you. Could you have predicted that this shape was going to be vertically aligned, meaning a symmetry at pi over 2? Could you have guessed that before I graphed it? Do you think that you could have guessed beforehand that the y-axis was going to cut this graph in half?
No.
No? Well, you can now. Now, why can you? Because this word here, sine. Sine, it means what variable?
What?
No why.
Y. You know, I should be putting this over here because that's the polar graph. Sine means y, which in polar, we don't say y, we would say theta equals pi over 2. This graph was always going to have symmetry with the pi over 2, theta equals pi over 2 axis because it was a sine. Not only that, you see how this is a negative sign? That's why this graph went down. Those things are always true. Sine is always going to be vertical. Cosine will have vertical symmetry. Cosine will be a horizontal, it's called polar axis symmetry. And so we're going to finish up just showing on the calculator over here. I believe if I'm right, the equation was 2 minus 5 sine. Let me turn off the rectangular graph. Do you see how we have that looped limacon like I was telling you? Now I want to change my equation. If I make this a plus, it's now going up because it's a positive sign. But my problem wasn't plus, it was a minus, so it was down. And finally, if we did not want this to be a sine, if it were a cosine, you'll notice the graph won't go down anymore. Let me go backspace, backspace, backspace. C-O-S. Notice now, if you look at it as a cosine, it points left and has symmetry with the polar axis, which is like the x-axis that would cut in half. That's a negative cosine. A positive cosine would obviously go to the right. One more thing before I wrap it up. Now let me show you the rectangular equation. Make sure we graph that right. S-I-N, there we go. Okay, here's my graph. Now let's pause the polar. Let's look at the rectangular. Notice we graphed this correctly. And as we said, we twice hit the pole because I have 2 x-intercepts. 2 x-intercepts means I hit the pole twice. I hit the pole. Where's my pen? I'll get a different color. I hit the pole on this path once, and then I hit it twice going there. I hit the pole twice because we had 2 x-intercepts. I only had 1 maximum, and that's why this graph appears to only have 1 maximum way out there. The minimum value of -3 is the inner loop. That was on the 3rd circle. That was the -3. This, that's an R value. This is the maximum R value of 7. And that's how it corresponded to the graph. So that's the only one I'm going to look at here. I've got plenty more. Do you have any questions for me before we sign off of this thing?
No.
No.
All right, I don't want to keep your time, so let's just, what would this have symmetry with? X-axis or Y-axis?
The x-axis,
Very good. Why?
because it's a cosine graph.
Okay, what about this one?
Why?
Y-axis.
And this one?
The
Y'all
cosine.
got it.
I mean, x, sorry.
You got it. Good job. Ran out of time. I didn't get to work these two. But I hope you have a good evening. and look forward to seeing you later this week.
Bye.
See you tomorrow, Mr. Voorhees.
See ya.